Hello, welcome to my help videos for AQA A-level chemistry. Hopefully you've used some of the other videos as well. If there's any videos missing that you'd like, please let me know. This one will focus on 3.3.7 optical isomerism. It's a very short topic, and the main thing that this fits in is it kind of fits in with other organic topics. Now, in AS, you look at isomerism and you define the term isomerism. You also look at one type of stereoisomerism, which is geometrical. You see that with the EZ in alkenes. You also looked at structural isomerism and three different types. Okay, so look out for an AS video on that, or review your work on AS. But this one focuses on optical isomerism. Okay, it's a new type of isomerism that you haven't come across before, and it comes up right at the beginning of second year A-level, and you use it within aldehydes and ketones, and you also use it again, you'll see it in transition metals. As always, start with the spec. So this is just literally copied from the AQA specification. You can see there's not much to it. It's kind of information as always, and the big important bits when it comes to the exams is this section. Students should be able to, so you should be able to draw structural formulas and display formulas for enantiomers and understand racemic mixtures, racemates are formed and how they are optically inactive. So we'll kind of look through all these phrases and these terms. Now, all molecules have mirror images, and for most molecules, so if I just pick a molecule, here we go. Just a molecule here. I've randomly picked a molecule. There we go. Dichloromethane. We could draw the mirror image for dichloromethane, and these two things would be exactly the same. Okay, they would be superimposable. If you were to make these out of molymods, they would literally be the exact same thing. Okay. However, for some molecules, the mirror image is not the same thing, and these two molecules would be said to be non-superimposable. And I'll draw a molecule that's not superimposable. Again, I doubt you've got molymod kits, but if you have, feel free to make these two, and you'll recognize that they don't. If you don't have molymods, you can use matchsticks and sweets or something. You can make these two models, different colored sweets for the different atoms, and you will find that these two things are definitely non-superimposable. Remember, when we draw these diagrams, this wedge, this is our attempt at drawing a 3D tetrahedral structure. Very rough, but this wedge is to show that this CH3 group is coming out of the page, and this dashed line is to show that this F molecule is going into the page. These two straight lines are showing that they're in the same plane as the page. So these three atoms, if you like, are on the paper. The CH3 is coming out of the paper, and the F is going into the paper. They are non-superimposable, those two atoms. The easiest analogy is if you were to try and put your left hand and your right hand together. If you put your two hands together, they appear to be the same thing. They are mirror images of each other, but they are non-superimposable. Your left hand is not the same as your right hand. Okay, they are mirror images of each other. They are non-superimposable. Going to look at some key words now then. Some 5 words that pop up. Now, the first 3 kind of link together. An asymmetric carbon or an asymmetric molecule and a chiral carbon, or the molecule displays chirality. Now, this is when we've got 4 different groups bonded to a carbon atom. Remember, this is organic chemistry. Carbon is a very common atom within organic chemistry, and carbon will always have 4 bonds, but not necessarily 4 different groups. Now, just be careful here, as some mistakes that people make is they might think that something like C2H5 and CH3 are the same group. They are not the same group. Yes, they're both bonded to a carbon atom, but an ethyl group is different to a methyl group. They are different groups. So it's not different atoms, it's different groups. Okay, and if you have a carbon that is bonded to 4 different groups, such as C2H5, CH3, so an ethyl, a methyl, we could have hydrogen, and then the 4th atom could be a halogen, for example. That would be an asymmetric molecule, and this is classified as our chiral carbon. Okay, so that molecule has or displays chirality. It has a chiral carbon. It's an asymmetric carbon. We could draw the mirror images because they are not the same thing. So as soon as you recognize a chiral carbon, that means it does display optical isomerism. And that is saying that those 2 molecules are mirror images of each other. They are non-superimposable. They are not the same thing, despite having the same 4 groups. They are non-superimposable. They would be classified as optical isomers, and these 2 isomers here are the 2 enantiomers. We've got 2 enantiomers here. Okay, you would have called, for example, in your geometric isomerism, in your geometric stereoisomerism, you'd have actually gone one step further and named them E and Z. We don't actually require naming of these. You will see it in some textbooks as D and L, or plus and minus, to distinguish between the 2. We don't need to be able to name the 2 enantiomers. We just need to recognize that those would be the 2 enantiomers, and that's what we've got. Okay, we've got 2 different enantiomers. We don't need to go a step further and name them. Okay, we do need to know how to distinguish between them, but that'll come up later on a later slide. So the enantiomers, that's the name given to the 2 isomers as a result of the chiral carbon. And a racemic mixture means that we've got an equal mixture of the 2 enantiomers. So if you've got a racemic mixture, you've got 50% of one enantiomer and 50% of the other. It was a racemic mixture, an equal mixture. Okay, what I'm going to get you to do then is I suggest you pause the video and have a go at this yourself. So what you're doing here is you've got 4 molecules, we've got propan-2-ol, we've got 2-chlorobutane, 1-chloropentane, and 3-methylbutane. I suggest you draw these out. Maybe practice doing structural formula, displayed formula, and skeletal. So draw the 4 of them out. Have a look along to see if you can find a chiral carbon. If you can find a chiral carbon, that means it has optical isomerism and it could be optically active. Okay, so draw them out. Literally go through each carbon in turn and identify how many different groups it has attached to it and if it has a chiral carbon or not. Okay, so I suggest you pause it now and you do that, and then you press play and you'll hear me go through it. So pause the video. Okay, so I'm going to draw displayed formula because it's usually the easiest to see, but again, be careful because you might be dictated to, you might be told that you have to use skeletal or you have to use structural. So I'm going to draw propan-2-ol, 1, 2, 3 carbons long with an OH on that second. I'm not going to draw all the hydrogens, but we've got hydrogens in each of those. So first of all, does this carbon have 4 different groups? Well, definitely not, because it's got 3 H's. So instantly it can't be a chiral carbon. So that's not a chiral carbon. This carbon, well, it's got an OH at the bottom. It's got an H at the top, but it's got 2 CH3 groups either side. So these 2 groups are actually identical. So that's not a chiral carbon. And the carbon on the end here, it has 3 hydrogens, which are obviously all identical. So that's not a chiral anyway. So A is not optically active. Okay, it doesn't have a chiral carbon, it's not optically active, does not display optical isomerism. Right, B, 2-chlorobutane, 1, 2, 3, 4, 2-chloro, there we go. I'm not going to draw the hydrogens, but I'll draw the bonds. Instantly, it's very easy now to discard these CH3s because they have 3 H's on them, can't be a chiral carbon. Likewise, a CH2 can't be a chiral carbon because it's got 2 hydrogens. This one's looking promising though here. It's got a H, it's got a Cl. it's got a CH3 and a C2H5. Remember, these two groups are definitely not the same as each other. C2H5 is definitely different to a CH3. So this is a chiral carbon. So this carbon here is definitely a chiral carbon. Now I need to draw, I've been asked to draw the enantiomers if it does display optical isomerism. So I'm now going to draw this chiral carbon and I'm going to show it as a 3D tetrahedron. So there's my tetrahedral structure. Now it doesn't matter on my first molecule where I draw the four groups. I just need to draw the four groups on. I know the four groups are H, CH3, C2H5 and Cl. So it doesn't matter, I can draw those in any order I like. It does become important though when I want to draw the enantiomer of that. So that's one of the enantiomers that I've drawn. So now it is important where I draw these bonds. I must ensure it's a mirror image. So look at this dash, it's mirror imaging the dash on the other side. The wedge, again, is a mirror image of the wedge on the other side. And we're going to mirror it. So I've drawn the bonds as a mirror image. Notice how the bonds are different. The dashed line is on the left here because it was on the right here. And now I must reflect those groups. At the top there's a H, this is a CH3, this C2H5, and this is a Cl. I've now drawn both enantiomers. Okay, I've drawn two enantiomers there. Again, if you're fortunate enough to have Molly mods, make them and you'll see that they are definitely enantiomers. Okay, moving on. C, 1 chloropentane. 1, 2, 3, 4, 5. 1 chloro. I won't draw the hydrogens on. Here we go. And I'm already thinking quite quickly ahead. CH3 can't be chiral, CH2 can't be chiral, CH2 can't be chiral, CH2 can't be chiral, and CH2 can't be chiral. So it was pretty quick and easy to recognize that there are no chiral carbons here. So 1 chloropentane is not optically active because it doesn't have a chiral carbon. Right, finally 3-methylbutane. 1, 2, 3, 4. 3-methyl, there's a methyl here. I'm not going to draw all of the H's on again. Not chiral, not chiral, not chiral. This one is looking promising. Yes, this is chiral. It's got a CH3, it's got a H, a CH3. Oh, hang on a minute, it's not chiral. It's got two CH3 groups. See, almost caught me out there. Doesn't have a chiral carbon. So this one is not optically active either. Okay, I'm going to point out now that if it doesn't have a chiral carbon, it's definitely not optically active. But we can't just assume that because it does have a chiral carbon, it is optically active. It just means it could be. And I'll point that out in a bit later on when we look at what we mean by optically active. Okay. Time for a quick recap then, some revision of some AS as well. So there's 4 definitions I'm looking for. So pause the video and have a go at those 4 definitions. And also down the bottom there, we've got 2 molecules, pentan 1-ol, pentan 2-ol. I want you to let me know or to find out if it has a chiral carbon, and if it does, to draw the 2 enantiomers. So pause it now, 4 definitions, and that question at the bottom. Okay, stereoisomer. This is the same molecular formula, same structural formula, but a different arrangement in space. Different arrangement in space. So that's our stereoisomer. Geometric and optical, they're both stereoisomers. They are forms of stereoisomer. The geometric isomer was different arrangement in space due to the non-free rotation around a carbon-carbon double bond. So we saw the geometric was different arrangement in space, which was due to the non-free rotation around a carbon-carbon double bond, which gave rise to the E and the Z isomers. And we actually had to assign priority rules and determine EZ on those alkenes. Optical isomerism we've just covered. So optical isomerism, they are 2 non-superimposable mirror images due to a chiral carbon. So we have 4 different groups on a chiral carbon. Therefore, it gives rise to non-superimposable mirror images, which is said to be optical isomers. chiral carbon. A chiral carbon is a carbon with 4 different groups attached to it. Don't say 4 different atoms or 4 different bonds, okay? Common mistakes made there. A chiral carbon is a carbon with 4 different groups attached. Do either of these two have a chiral carbon? Well, let's construct pentan 1-ol. Pentan 1-ol, there we go. 1, 2, 3, 4, 5, pentan 1-ol. Well, that's a CH3, that's a CH2, that's a CH2, that's a CH2, and that's a CH2. So none of those chirals are, sorry, none of those carbons are chiral. Pentan 2-ol. Again, I can very quickly get rid of the CH2s and the CH3s. CH3s, CH2s, definitely not chiral. This one, however, is making me think because it has a CH3 group attached to it. It has an OH group attached to it. It has a H attached to it. And it has a C3H7. So this is in fact a chiral carbon. Okay, so now let's draw the two enantiomers. So I draw my carbon as a tetrahedral. There we go. So this now is my chiral carbon here. I'm going to draw the 4 groups. Again, it doesn't matter. I can randomly draw. I know my 4 groups, OH, H, C3, H7, and a CH3. It does not matter where I place those 4 groups, as long as I place the correct 4 groups on that molecule. It does matter, however, when I go to draw the enantiomer. So I'm going to draw the plane of the mirror. And now I'm careful where I draw my bonds. There we go. Making sure that it's a mirror image. And now I just reflect the groups. So C3H6 at the top. On the wedge, it's CH3. On the dash, it was OH. And over here, it was H. So there's my 2 enantiomers. Right then, so final thing. Enantiomers do have identical chemical and physical properties. Only 2 things, though, you're going to find that that's not the case. So there's 2 exceptions to that. How they affect plane polarized light, and we'll talk about that. Okay, so plane polarized light, I'll talk about that in a minute, and also their reactions with other chiral molecules. Now, plane polarized light, physicists amongst you will recognize what that means, but I'll just try and clear it up. You don't need to know this, in all honesty. You don't need to know what plane polarized light is, but it helps your understanding if you do. So plane polarized light. Now, light travels in transverse waves. Okay, that means from GCSE physics that the displacement is perpendicular to the direction it travels. In other words, if light travels from A to B, it travels in one direction, the displacement will be up and down as it travels from A to B. Okay, now if you were to kind of look down that tube of the light traveling, you'll actually find that it will be displacing up and down, left and right, up in all different possible scenarios. However, plane polarized light will only be in one direction. Plane polarized light, the light is literally displacement in one up and down, or left and right, just plane polarized light. Now, if you pass this plane polarized light through a sample, so let's just say we pass the plane polarized light through a solution containing 1 enantiomer, then what happens is the plane polarized light is actually rotated and it comes out, displacing the displacement being slightly different to how it went in. So if you pass it through one of the enantiomers, it will rotate plane polarized light. If you were to pass it through the other enantiomer, and again we don't need to name them, they're the D and the L, or the plus and the minus, we don't need to know that. But if you pass it through a different enantiomer, it would rotate it the other way, anti-clockwise. Okay, so the enantiomers will rotate plane polarized light in different directions. And this is where the term optically active comes from. It's optically active if it rotates plane polarized light. So if you don't have a chiral carbon, it won't rotate plane polarized light. But what you have to be careful with is if we do have a racemic mixture, if your mixture contains equal amounts of both enantiomers, then what's actually happening is one enantiomer will cause it to rotate clockwise, whilst the other enantiomer kind of cancels that out and cause it to rotate anti-clockwise. And therefore, if you've got no effect, if the plane polarized light is not affected, that means one of 2 things. It means it doesn't have a chiral carbon, or it's a racemic mixture. And they love this in the exams. They love to try and catch you out by asking, why is it not optically active? And people just instantly want to say, because it doesn't have a chiral carbon. But that's not the case. If it's not optically active, it means either it doesn't have a chiral carbon or it's a racemic mixture. And you will definitely see this in our aldehydes and ketone reactions in the next topic. Okay, so just be aware of that. But that's what optically active means. It means passing it through plane polarized light, and it either rotates, in other words, it is optically active, or it doesn't rotate and it's not optically active. So that's how we can test to see if something is optically active. And finally then, their reaction with other chiral molecules. So enantiomers will react differently with other chiral molecules. So for example, you're talking an awful lot about lock and key in biological processes, and the idea is that one specific type of one of the enantiomers will kind of fit the lock and key. And if you can imagine your mods, if you've made these, so to make your chiral molecule, one of them will fit the lock and key, one of them will not. Okay, so that's very important when it comes to the drug industry and biological processes, because one of these would react differently to the other in a biological process, for example. Okay, and I'm just making this molecule up. I think I used it as an earlier example. So those are some things to look out for. Okay, so those would be two enantiomers. They would behave differently if they were reacting with other chiral molecules, which is the case in drugs and biological processes. Okay, so hopefully that was useful. Again, let me know of any other videos you want, and good luck.